Welcome to Ostino Educational Center. In our previous lesson, we talked about empirical and molecular formula determination. And then we pointed out that in an empirical and molecular formula determination, which is the key part of determining the chemical composition, the element of organic compounds. So in our organic chemistry class today, we are going to be looking at empirical and molecular formula determination. In our previous video, I pointed out that empirical formula and molecular formula shows the simplest and the actual whole number ratio of each element present in certain organic compounds. And for organic compound to exist, we say that carbon, major element in organic compounds, must be present. And then how can carbon be determined empirically? That is what led us to what we describe as determination of empirical formula and molecular formula of these compounds. And so therefore, today we are going to be dealing with the mathematical of how empirical formula will be determined, and then looking at different examples of how empirical formula questions and molecular formula questions are determined and then solved. And so therefore, in our previous video, I pointed out that there are 3 steps in determining empirical and molecular formula. One of those is determining the relative atomic mass of each atom present in the compound. And number 2 is determining the percentage composition of each of those atoms present. And then finally, the ratio of those atoms present. And so today we are going to be looking at certain examples that will aid us to see how we can use these 3 steps in arriving at different empirical formula. And so therefore, I urge you to give me your attention, stay tuned, and subscribe to this channel for more interesting topics. And so in our today's question, we'll be looking at the question that relates to combustion. And I said that this empirical and molecular formula can be determined for an organic compound that's said to be an unknown that undergoes chemical combustion. We can use the product of this combustion to actually determine which organic compound actually went through those combustions. And so we're looking at question number 1. All right, here before us is question number 1. This question comprises of the percentage composition, the weight, and then the ratio before getting the empirical formula. Now, all right, looking at the question, we have 0.404 grams of compound A, an unknown compound, gave 0.722 grams CO2 and 0.294 grams water. What is the empirical formula of compound A? With this question, you are expected to go through the 3 basic steps, which is getting the weight of each element present, getting their composition of each element, getting their ratio before arriving at their empirical formula. So from the question, we look at solution to the question that via chemical reaction, we are looking at that it went through combustion and then produces CO2 and then water. And I have said it before that all organic compound that undergoes complete combustion will give us CO2 and water. Complete combustion. Take note, complete combustion. If the combustion is not complete, you will not have CO2 and water. You will have CO, carbon monoxide, and not carbon dioxide, and then water. For a complete combustion of all organic compounds, all hydrocarbons will give us CO2 and water. And so, taking it that a compound A gave CO2 and water, we already know that that compound is an organic compound, an hydrocarbon, making up of carbon, hydrogen, and oxygen. Right now, A undergoing combustion, we have CO2, and then from the question we are given that the CO2 by weight is 0.722 grams, and then the water by weight is 0.294 grams, and then the unknown compound that went through the combustion was 0.404 grams. This is a simple equation, and then we are asked to find what is the actual compound that went through the combustion, which is what is the empirical formula or the empirical compound that undergoes this combustion to give us CO2 and water. And we say that from our previous video, we emphasize that for us to be able to get the empirical formula, there are three basic steps. Which one? Atomic mass of the element present. All that, the relative molecular mass of the compound. Now, this compound is the compound that the element in question is found in. For instance, here we are looking at carbon. If you look at carbon here, after getting the relative atomic mass of carbon, we will get the relative molecular mass of the compound that carbon is present in, which is CO2. So we get the relative atomic mass of CO2 times the weight of the compound that the element is found in. Like in this case now, weight of CO2. So from this, we can deduce that the weight of the relative atomic mass of carbon is 12, and then the relative molecular mass of carbon of CO2 is 44. So we have that multiplied by the weight of CO2, which is already given to us as 0.722 grams. If we do this mathematically, we are going to be arriving at the weight of carbon present in the unknown compound A. And then if we do that mathematically, we are going to be arriving at 0.196. 0.196. Going through the steps, like you have mentioned, relative atomic mass of each element present, all over, relative molecular mass of the compound in which the element is found in, multiplied by the weight of the compound in which the element is found in. That will give us the weight of the element that we are looking for. And so for instance, this is the weight of carbon, and then it's already set into the 0.196 from our mathematical expression. We have 0.196 grams. All right, we'll do that for hydrogen. Hydrogen, in this case, is already there. Hydrogen is there, and then we have that the relative atomic mass of hydrogen is 2, all over. The relative molecular mass of the compound in which hydrogen is found in water is 18. multiply by the weight of water, which is given to us in the question as 2.94 grams. All over 1. If you do that, that will give us the weight of hydrogen present in your known compound. If you do that mathematically, you are going to be arriving at the weight of hydrogen, which is already given to us as, if you do that mathematics, you will be having 0.032. And then (0.032 grams as weight of hydrogen. Now, weight of carbon, weight of hydrogen has been found. Weight of oxygen as the third element present in the compound, in the unknown organic compound, can be determined by simple mathematical expression. Knowing too well that CO2 has oxygen, water has oxygen, so we get the weight. What is the overall weight? So that will give us that the weight of oxygen will be equals to the overall weight of the unknown compound minus weight of carbon plus weight of hydrogen. This will give us the weight of oxygen. So if we do that, we already have that overall weight is 4.04 grams minus weight of carbon is 0.196 grams plus weight of hydrogen is 0.032 grams. So already we have that. If we do that mathematically, we are going to be arriving as the weight of oxygen to be 0.176 grams. 0.176 grams as the weight of oxygen. So each element in the unknown organic compound has been determined in terms of their weight. So step 1 is done. Getting the weight of each element present. Getting the weight of each element present. So we have gotten the weight of carbon to be 0.196, weight of hydrogen to be 0.032, and then of course weight of oxygen to be 0.176. From there, we get to step 2. Step 2. In our step 2, we'll be looking at the percentage composition of each atom present. So how do we get percentage composition? Like we previously mentioned, that we get the weight of the atom or element all over the overall weight of the unknown compound. Weight of the unknown compound times 100 over 1, because we are dealing with percentage. So weight of the atom present, we do that for each of the atom, knowing too well that by that formula we are going to be calculating for carbon, percentage weight of carbon, C, will be equals to weight of carbon is already known to us to be 0.196 all over. Overall weight of the compound from the question is given to us as 0.404 times 100. Do that, you are going to be having the percentage of carbon. If you do that mathematically, you're going to be arriving at 48.5%. 48.5% carbon. Same weight of hydrogen. Of course, the same thing, weight of hydrogen is already given to us 0.032 grams all over 0.404 overall weight of the unknown compound times 100 over 1, because we are doing a percentage. Working that, we should be arriving at 7.9%. 7.9%. 7.9% for hydrogen. So you can see we have determined the percentage composition of carbon in the unknown compound, percentage composition of hydrogen in the unknown compound, and then what is left there is percentage composition of oxygen. Knowing too well that oxygen is as well present in both compounds CO2 and water, arriving at the percentage composition of oxygen will be equals to formula 100 minus percentage composition of carbon plus percentage composition of hydrogen. That is the formula we apply. And then if we do that, we already know that 100 minus bracket open, percentage composition of carbon is given to us as 48.5, and then that of hydrogen is 7.9, or in percentage. If you do that mathematically, you are going to be arriving at 43.6%. 43.6% for oxygen. So step number 1, determining the weight of each element present in the compound, and step number 2, getting the percentage composition of each element present has been done. Of course, carbon is already given to us as 7.9, as 48.5, and then hydrogen is already given to us there as 7.9, and then oxygen, by our calculation, we arrived at 43.6%. So the next step is the ratio, which is the last step, but this step is critical because you must be very careful in your ratio. If your ratio is not properly done, then you know that you may get your empirical formula wrong. Any step missed at the ratio point, the formula is wrong. And so in that case, we arrive at the ratio. Step number 3, ratio. Step 3. And that's the last step I mentioned in a previous video. I pointed at these 3 steps. I said when you get to this point of the ratio, you got to be very careful in deciding which step you take in terms of rounding up and rounding down the number, especially if it deals with fraction. Alright, so let's take our step. From our ratio, we say that the ratio is going to be percentage composition. Percentage composition of each element. Divided by their relative atomic mass. Take note. Percentage of each of the elements divided by the relative atomic mass. Alright, so we set up our percentage, we set up our ratio. So for this, bring out the elements in question. What are the elements? We have carbon, we have hydrogen, and then of course we have oxygen, all in ratio form. For carbon, what is the percentage there? We have 48.5%. 48.5% for carbon. And then for hydrogen, we have 7.9%. For oxygen, we are already having 43.6%. These are ratios. So from our formula, divide by the relative atomic mass of carbon is 12. Relative atomic mass of hydrogen is 1. The relative atomic mass of oxygen is 16. So they are done. Formula. Go back. Come down here. Be very careful in dealing with this. If we go by this, we already know that hydrogen is going to give us back 7.9. 48.5 divided by 12. If you go that, you are going to be having what we describe as 48.5 divided by that. We'll have 4. And then 43.6 divided by 16 will give us 2.7. Very importantly, at this junction, you can see we have a fraction throughout. There's a fraction there. 7.9, 2.7 fraction. Just one whole number. Step 1. First of all, you must divide through. You must divide through. Divide through by the smallest number. You must divide through by the smallest number. So when we divide through by the smallest number here is 2.7. So we divide all through by 2.7. 2.7. 2.7. So if 2.7 go with 2.7, we are going to be having 1. And then 7.9 by 2.7, we are going to be having 2.9. And then of course, 4 by 2.7, we are having 1.5. Very important. That's why you must be very delicate in making the choice. So we have still fractions there. We are still having fractions there. At this point, decision making solely depends on, first of all, checking through that when you multiply through after division, when you multiply through by a certain whole number, that you will have a whole number. Alright, then getting to this point where decision is solely depend on the fraction that you have at the end of your division. Now, looking at these fractions, we already know that we cannot round up 1.5, knowing too well that if we multiply 1.5 by a whole number of 2, we are going to be getting 3. So multiplication takes precedence over rounding up or rounding down, except in a case where when you multiply by a certain whole number, you will never get any whole number in the composition. But when you know that multiplying by a certain whole number will give you a whole number, ensure to do multiplication before rounding up or rounding down. And so in that case, we are going to be multiply through by 2. So if we do that, we'll be having 3 here, and then here we'll be having 5.8, and then here we'll be having 2. At this point, we can round up and round down, because if we keep multiplying, we can never get whole number. And so in this case, we are going to be having, rounding up this one will give us 6. And so our empirical formula our empirical formula for carbon is going to be 3. For hydrogen, it's going to be 6. And then for oxygen, it's going to be 2. And so our empirical formula is equal to C3 H6O2. This is an organic compound that went through combustion reaction to give us CO2 and water. So this is compound A that went through that combustion reaction. And so with this, you can actually get some structures from this. Alright, our next example will be looking at another dimension of determining empirical and molecular formula. Stay tuned. Looking at example number 2. This example number 2 is similar to the previous example, but is more technical. 0.029 grams of an organic compound containing carbon, hydrogen, and oxygen. Like we previously said, they are the major elements that constitute organic compounds. Only gave 0.058 grams of carbon dioxide and 0.024 grams of water on combustion. The molecular mass of the compound as determined by experiment is 88. That is the molecular mass, that is the molecular weight of the compound. The compound did not react with phosphorus trichloride, meaning that compound did not react with PCl3. But lithium aluminum hydride, a reducing agent, very strong reducing agent. Lithium aluminum hydride. But lithium aluminum hydride reduce the compound to give an ethanol. What is the percentage composition of the compound? B, empirical formula. C, molecular formula. And D, structural formula. So we are asked to not only determine empirical formula, molecular formula, as well as the structural formula, and of course, percentage composition. This as well will simply undergo the 3 basic steps of determining empirical and molecular formula, which is 1, finding the relative atomic mass of the compound and the relative molecular mass of the compound times the weight of the compound in which the element is in. That will give us the weight of the compound. So first of all, the first step is getting the weight of the compound, weight of each element, getting the weight of each element. Of course, from the question is already identified. Previous question they didn't tell us that, but this question they pointed it out as carbon, hydrogen, and oxygen. Right now, we need to get the weight of carbon, the weight of hydrogen, the weight of oxygen as previously determined. Same step, same method. We are going to determine the percentage composition, which is part of the question we are asked to do. Step 2. And of course, getting percentage composition, all you need to do is to get the weight of the individual element over the weight of the overall compound times 100/1. Then, finally, we go to step 3, which is the ratio. Like we did previously, the ratio is where you have to be very careful about, because when you fail the ratio, the empirical formula is wrong. When the empirical formula is wrong, the molecular formula will be wrong. And when the molecular formula is wrong, the structural formula is wrong. There is no two ways about it. There is no magic within it. It must follow systematic steps, because science has to do with step-by-step method. You can't jump step 1 and get step 2. You must follow due process. And so, in chemistry, you must ensure, especially in organic chemistry, that steps must be followed. Any step that is altered, everything is destroyed. And so a chemist can destroy millions of persons. Chemistry can destroy millions of persons. And so it's very paramount that you are careful in dealings, both calculation in chemistry, both reactions in chemistry. You must be careful with them, because any step or change can lead to explosion or lead to death of certain individuals. Alright, so right now we'll take our steps, and then very quickly we'll look at them, and then we'll try to manage our board and then manage them very well. So we'll have our board so we can see our question and then see how we can get them done. And so in this case, getting the weight of the compound previously, like we said in our previous example, weight of the element is equals to RAM, which is relative atomic weight or mass of the element, all over relative molecular mass of the compound in which the element is found, times weight of the compound in which the element is found. When you do that, you get that. So we'll do that each element. So quickly, we'll say weight of carbon will be equals to relative atomic mass of carbon is 12. Molecular mass of carbon is found there is CO2, of course, is 44. Multiplied by the weight in which carbon is found. CO2 from the question is given to us as carbon dioxide is 0.058. So we have 0.058 grams. So that's the weight of CO2. CO2 because carbon is found in CO2. And so when you do that, express that mathematically, you are going to be arriving at 0.015. 0.015 grams of carbon. And so quickly, you do that for our friend hydrogen. Hydrogen is already given to us 2 relative atomic mass all over relative molecular mass of the compound in which hydrogen is found, which is water, is 18, times the weight of water in the combustion reaction, which is 0.024 grams. When you do that, you do your mathematics properly, you are going to be arriving at the weight of hydrogen in that particular question. So that will give us 0.00226. 0.00266 grams. So same thing there, of course, like we previously made sure in our previous example, that weight of oxygen will be equal to, of course, overall weight of the compound, which is given to us as 0.029 minus bracket open weight of carbon, which is 0.015 grams, plus weight of hydrogen, which is 0.00266 grams. When you do that, we are going to be arriving at the weight of oxygen in that question. And then quickly, we'll move down to step 2. That will render us to the question number A, which is percentage composition of the element. So when you do that, mathematically, the weight of oxygen present in the compound will be given to us as 0.011. So this will give us 0.011 gram. So the weight of individual element present in the unknown compound is determined mathematically. So we already have carbon 0.015, of course hydrogen 0.00266, and of course oxygen 0.011 grams. So step 1 is done. Okay, so we are going to be moving down to step 2. Moving down to step 2. Step 2 is getting the percentage composition, which is one of the questions we are asked to find. And getting the percentage composition is as simple as, of course, from our step 2, percentage composition of each element present or atom present divide. Okay, so percentage composition of each element, that's what we are going to be finding. So mathematically that can be expressed as weight of the element all over overall weight of unknown compound times 100. So we'll do that quickly for carbon. Percentage composition of carbon in the compound. What is the weight of carbon there? We already have it to be 0.015 grams. All over overall weight of the compound is given to us 0.029 times 100 over 1. So do that. Same to that of hydrogen. We already have that to be 0.00266 all over 0.29 times 100 over 1. So we are going to get this. So when you do this mathematically, we arrive that the weight of carbon is 54.48. 54.48. 54.48. 54.48 grams. Sorry, not grams, percentage. Alright, when you do that for hydrogen, we are going to be having 9.17. 9.17%. And then, of course, same method as previously mentioned as for oxygen, 100 minus bracket open, 54.48 plus 9.17 or in percentage. That will give us that of oxygen. Working this, our percentage of oxygen will be 36.35% for oxygen. So finally, we are almost wrapping up the percentage composition of all the elements. So question number A has been answered successfully. Question A has successfully been dealt with. Question A among questions we are asked to work on. Okay, so from question number A, we have it to that percentage composition of carbon there is 54.48. Percentage composition of hydrogen is 9.17. Percentage composition of oxygen is 36.35. So this has answered question A. But we need to move to question B, which is the empirical formula. Now, going through that, we have to go to our next step, which is ratio. Step 3. Step 3, ratio. Now, by our ratio, it is that percentage composition divide by the relative atomic mass of each atom or element present. So that's how we get our ratio. So doing that, bringing in our element carbon, hydrogen, of course oxygen. And the ratio of carbon is to hydrogen is to oxygen. So bringing our present composition by our previous step 2, carbon is 54.48, and then hydrogen is 9.17, of course 36.35%. So the rule is divide them by their relative atomic mass. Like this is 12, and of course this will go with 1, and then of course this will go with 16. Expressing this mathematically, we'll have that if this go with this, we are going to be having 9.17. So 12 into 54.48, we are going to be arriving quickly at 4.54. 4.54. And then 36.35 divided by 16 will arrive out as 2.27. 2.27. Remember, as previously mentioned in the previous examples, example 1, you must divide through by the smallest. Divide through by the smallest, of course. If we divide through by the smallest, divide by the smallest number, we have this to be 2.217, 2.27, and of course 2.27. 2.27 we go to 2.727, we have 1, and of course 2.27 into 9.17, of course we'll be having 4.03, and of course if this goes into this, we're going to be having 2.2.0, so we're having 2.0. So they're already a whole number. At this point, you don't need to multiply through by any whole number, just like we previously said in the example 1, where we multiply by whole number. At this point, they are all, you can make them whole numbers. This is 2.0 is 2, 4.03 is 4, and then 1. So we already have it to be 2 is to 4 is to 1. So our empirical formula, which will answer our question B from the question, our empirical formula which will be C2, of course, H4O. This is equals to E dot F. The next step is to move to the molecular formula, question number C. Like I said, step at a time. So going through that, knowing too well that question number C is asking for N dot F, and from our previous video, we pointed out that the molecular formula is equal to empirical formula multiplied by N, where N is a whole number ratio. Where N is a whole number ratio. Alright, we have our empirical formula. We don't have our N. We can find N. So how do we get that? We come in there, N dot F will be equal to, what the empirical formula is? C 2 H4O bracket N, which is equals to the molecular weight, molecular mass of the compound by experiment was determined to be 88. So this whole thing will be equal to 88. So we need to find the empirical weight. This is the molecular weight. We need to find empirical weight. So empirical weight can be determined from the empirical formula. and empirical molecular weight can be getting from a molecular formula. So how do you get that? Since your empirical weight is known, you can get it there. So our empirical weight will now be equal to this. Carbon is of course 12 times 2 plus 1 times 4 for hydrogen plus 16 equals to 88. When you do that mathematically, you are going to be arriving that 2 times this is 24 plus 4. 1 times 4 is of course is 4 plus 24. Of course we have 28 plus that 16. So 28 plus 16, we're going to be having 44. So we have that the n dot f will be equals to 44 bracket n equals to 88. Making n here subject, we are going to be having that n will be equals to 88 divided by 44. And that will give us 2. So when this happens, our n is equal to 2. And then bringing in our molecular formula will therefore be equal to, knowing too well that n dot f will be equal to E dot F. So we have that our E dot F is already given to us as what? C2 H4O bracket. Now our n there is 2. So it's going to be 2 into this. Of course, we're going to be having C4 H8 and of course O2 as our n dot f. So molecular formula is equal to C4 H8 O2, while empirical formula is C2 H4 O2. It doesn't end there. The last question is what is the structural formula of the said compound? What is the structural formula of the compound in question? Now, structurally, understanding that carbon, previously in our last videos, you can recall that I made mention that organic compound couldn't have been possible without the process of catenation. Carbon interacting with carbon to form long chain. And that is the long chain. It's forming now 4 long chain. Carbon interacting with carbon. And then it is when this concept came to existence that organic compounds started existing. So the existence of organic compounds came as a result of the ability of carbon to form catenation. That, like I previously said, was the unique property of the element carbon among the group 4 elements. After carbon in group 4 is silicon. And that is why silicon is resemblance to carbon. The only disadvantage is that silicon will give you an unstable compound when it comes to hydrocarbons. But carbon forms more stable compound because of the interaction. The bond between them is called covalent bond. And so this covalent bond are bonds that are held together by electrons equally shared by these carbon atoms. And so to bring out the structure, you must understand catenation. Catenation is the source where these things come from. So if you go by that, then we put 1 or 2 together, 1 and 2 together to get the result. Okay. Forming this, okay, get carbon to carbon. So carbon we have to bond to carbon. Carbon we have to bond to carbon. Carbon we have to bond to carbon. We have to bond to carbon. We have to bond to carbon. This is catenation. 4 carbon ejects. This process is what we describe as catenation. And apart from bonding to carbon, it also have ability to interact with hydrogen. That was why hydrogen was part of the composition of organic compounds through what we describe as hybridization. So there is an hybrid orbitals interacting, forming the bond we describe as covalent bond. And so, if we understood that properly, it means that this my carbon here, and this my carbon here, and this same carbon, we share 4 bonds. So one of the bonds we share with hydrogen, another one with hydrogen, another one with hydrogen. So this carbon already is saturated. The next carbon, we have another hydrogen here, another hydrogen, another hydrogen. The next carbon, we have another hydrogen, another hydrogen. We are gradually bringing out the structure. Let's see. 1, 2, 3, 4, 5, 6, 7. How many hydrogen is there? 8. And so we can keep going. 2 oxygen, so you can have 1 oxygen here, another oxygen here, with another hydrogen. So we have empirically and structurally formed a compound known as this. This is a carboxylic acid compound, and this is butanoic acid. If you understood the question vividly, this should be from the question. This should be the compound that actually undergoes the combustion to give carbon, hydrogen, and oxygen. Reasons are: it is carboxylic acid that undergoes reduction. From the question, they said, but lithium aluminum hydride reduces the compound to give ethanol. It is only carboxylic acid that can be reduced in the presence of lithium aluminum hydride to give alcohol. So, even if we know that other compounds can manipulate here, can bring out other compounds like the esters can come in here. The esters. You can also have that CH3, COO, CH2, and CH3. This is an ester functional. So this is the same thing with this. But the unique thing is that they are all carboxylic acid derivatives. Meaning they are all gotten from carboxylic acid by the reaction of the carboxylic acid functional group. Knowing too well that we can still get more of these compounds from here. An isomer of that. An alcohol with a ketone can be formed with this. Let's see how we can play around that. We can have CH3, CO, CH2, and then CH2OH. 1, 2, 3, 4. 4 carbon. 3, 5, 7, and 8. 8. How many oxygen? 1, 2. So this is another compound still deriving from this place. When we get to naming nomenclature, we play with the names. Because when organic compounds are not properly named, I don't think you can be able to understand the reactions. Because reactions of most organic compounds take place at the functional group. So I will urge you to stay tuned and subscribe to this channel for more examples. Thank you. Looking at another example of empirical and molecular. There are a lot of examples to look at when it comes to empirical and molecular formula. But critically, this example follows similar steps. And so holding on to these steps, you are 99% ready for any questions that has to do with empirical or molecular formula. Looking at the board now, we have example 3. A compound Y contains 87.5% nitrogen and 12.5% hydrogen by weight. It has molecular weight of 32.0 grams per mole. What is the molecular formula? At this point, they are requesting for molecular formula. You cannot jump 1 and get to 2. You must pass through empirical formula. So it is necessary that empirical formula must be determined. And then in this case, now it's not just a compound, but say compound Y undergoes that process. Now, looking at them, they are already in percentage. Putting these 2% together is already giving us 100, so there is no need bringing oxygen. So what it means is that this compound did not undergo combustion. So that makes them not to be organic. So they are not organic compounds, because if it's an organic compound that went that undergo this process, oxygen will be there. And that is why in our previous class and video, we have pointed it down with that number that organic compounds must undergo complete combustion to give us CO2 and water. Note, the combustion must be complete. Must be complete. We have incomplete combustion. We have partial combustion. This produces different compounds. But as long as that combustion is complete, it must give us CO2 and water. But in this case now, it's not giving us oxygen. There is no carbon there. So this alone has given us a signal that this compound Y is not an organic compound. But nevertheless, empirical formula and molecular formula can still be determined from them. So this is an inorganic compound. So empirical and molecular formula can still be determined from them, following similar steps. So irrespective of the question, as long as it deals with the empirical and molecular formula, these steps must be checked up. First, get the weight of each atom present. Second, get the composition of each of them. And then, of course, number 3, get the ratio. Very importantly, this has already been done. They have already given us percentage composition. So step 1 and step 2 is done. We are going straight to step 3, which is the ratio. So, in giving us, in our solution, we just look at the ratio. We have nitrogen and oxygen. So we have nitrogen and hydrogen as the ratio. What do we have for nitrogen? We have 87.5, and then divide by the relative atomic mass, and that is 14. And then of course, for hydrogen, we already have 12.5% divided by 1. So we already have this to be 12.5. And then of course, when 85 divided by 14, we have 6.25. 6.25. Remember, divide 2. Divide 2 by the smallest. And then that is 6.25. And then this will be 6.25. When this go with this, we have 1. Then of course, when this go with this, we have what? We have 2. So our empirical formula here will simply be N. But that was not what we are asked to do. We are asked to find molecular formula from the question. And then recall that in our previous example, we pointed out that molecular formula and empirical formula has a relationship mathematically as N dot F equals to E dot F, of course, bracket N, where N is the whole number ratio. And then, knowing too well that our molecular empirical formula is already determined as NH2. So we come here and say M dot F will be equals to bracket open N H2 to this. This molecular weight of the compound has already given to us to be 32. We have 32. So fixing this up, we have this will give us 1 times 14 plus 1 times 2 equals to 32. Doing this will give us 16 bracket N equals to 32. So where N will be equals to, of course, 32 divided by 16. That will give us 2. So fixing that here will give us that M dot F will be equals to NH2 bracket 2 equals to N2 H4 as our molecular formula of the same compound. A Y that contained 87.5% nitrogen and of course 12.5% hydrogen. So that is that. So in our next example, we'll be pointing out a critical part of the empirical and molecular formula. Okay, example number 4. Give the percentage composition of M if 2.58 milligram on combustion gave 5.87 milligram CO2 and of course 2.4 milligram water. Already from the product of this combustion reaction, we already know that the compound that went through that combustion M is an organic compound. Because the product is already giving us CO2 and water, and of course it's a complete combustion reaction. So knowing that, but the problem here is that not really a problem though. The challenge is the unit is in milligram, but that doesn't matter. Just slight conversion of units from gram to milligram. We use the same method, the same formula we applied in the previous one, but just that the units, if you want to put your units, it has to be in millimoles because, of course, it will be a change at the point. So we'll see where the change is coming from. So first of all, what we are asked for is percentage composition, not the empirical formula in this case. So all we need to do is to do step 1 and then step 2. Step 1 is get the weight of each atom or element present in the unknown organic compound. And then of course we know that will give us as the relative atomic mass of the elements in question all over the relative molecular mass of the atom of the compound itself, and then mass times the weight of the compound in question. So for example, we said for carbon in this case, weight of carbon in this case will give us, carbon here is 12 all over 44, which is the compound which carbon is found, CO2, times of course the weight of CO2 which is 5.87. Do that for hydrogen. Weight of hydrogen will be 2 all over 18, which is water. The weight of water there is of course 2.58 milligram. When you do this mathematically, you have that the weight of carbon there will give us 1.60 milligram. 1.60 is millimoles. It will give you millimoles. And then of course when you do this, this will give us nothing less than 0.267. 0.267. Of course it's the same unit. Same thing, of course, weight of oxygen will give us overall weight of the compound, which is low. This will give us weight of hydrogen here is 2.4. Overall weight, which is 2.58 minus bracket open. Weight of carbon, which is 6.0 plus 0.267 weight of hydrogen. When you do this mathematics, we will arrive certainly at 0.713 as the weight of oxygen. So mathematically, the weight of each element present has been derived. So step 1, all this falls into step 1, as previously mentioned in our last video. And I said that these processes takes similar steps. You can see all the examples, you can keep citing examples, keep looking for examples of empirical and molecular formula. They will all still fall into those 3 basic steps. So basically, if you have the steps in your finger tips, first of all, get the weight of each element. Secondly, get the chemical composition of each element by percentage. And then, of course, get the ratio. Empirical formula will just come up. Now, but we are asked to get just percentage composition. That's where we are asked to stop. So we are asked to stop at step 2. So by our step 2, we have that the weight, percentage composition of carbon will now be equal to the weight of carbon, which is 1.60 all over what? Overall weight of the compound, which is what? 2.58 times 100 over 1. Same to hydrogen, we have that hydrogen is 0.267 divided by 2.58 times 100. Do that mathematically, you have that the weight of carbon by percentage will given to us as 0.62.01%. And then, of course, that of hydrogen will give us 10.34. And then, usually, the compound contains oxygen on both sides. And so, percentage oxygen will be 100 minus bracket open 62.01 plus 10.34%. When you do that, you have 27.65% as oxygen. 27.65% oxygen. So we can go on and on and on and on empirical and molecular formula. In our next example, we are going to be dancing through the empirical and molecular formula involving gases. You know, organic compounds are not just liquid, semi-solid, they are also gases. And so what if the compound in question is a gas? So in our next example, we'll be looking at the empirical formula involving gases, gaseous compounds that undergoes combustion. Gas is born on heat, and if we can actually determine the empirical formula of the gas, the said gas that went through the combustion reaction. So that's the area we're looking at in our next example. And then we'll look at another complex example that has to do with empirical formula, so that we can beat our chest and say that we have actually dealt with empirical formula determination in totality. And so I urge you to stay tuned to Ostino Educational Center while we unveil the secret behind organic chemistry. Subscribe and turn on your notification button so that as we drop these videos back to back, you get to be notified on the information on the topics that we'll be treating step by step. After empirical formula, we'll be entering into a very interesting topic. So I urge you to stay tuned to this channel, subscribe, and share to your friends, relatives, colleagues who might be interested in knowing the history, the mystery behind organic chemistry. Thank you, and God bless you.